So, why are you not showing? My presentation, I kind of gloss over a lot of the basics because I assume they would be covered by now. So you have your input files, your need to change the orbitals, in the MATLAB code, the Z steps, and all that. So the first thing that I was looking at is the population of orbitals graphs, which Aaron covered a little bit. And so we see these population graphs, and much like Aaron said, you start out at your whatever you set your IE or IH at, which in my case I used HOMO -10 and LUMO +10. And I just picked those randomly for this presentation. So you see that the population decays and transitions from the higher energy to the lower energy ones, and eventually reaching the band edge. And my model is degenerate, so you see that I have multiple, that the two closest are occupied instead of just the HOMO. And we see the same features in the electron occupation. So if you would go through the MATLAB code, this code that I have up in the corner here is the code that generates these two graphs, or specifically the one I have generates this graph. This E would be an H to generate the whole graph. So and as Amir was complaining about, we have a nice way to determine how how it's labeled. Otherwise, yeah. Was there any questions on the occupation graphs? The waterfall graphs?
So Sean doesn't have questions. Kaya, Amir?
I don't know. I seem to have lost the chat when I started sharing.
Just say the dynamics look very interesting.
Yeah, I'm looking at this. This in specifically the electron in LUMO +9 and LUMO +8. I find a bit odd as I'm looking at this one.
It'll make for a good story.
But I literally just chose these orbitals at random when I did this so that I would have more than three waterfalls to look at, because So then we have our photoluminescence graphs, and so the code I have over here on the right is actually for multiple different versions of this figure. So the one you're looking at is specifically the first line of the first figure from this code. And there's just the different ones are just different representations of the different ways to represent the emission. So one thing to note with the code, and the reason I picked this specific one, is there's odd air with degenerate systems where we have this large intensity right at 0, because it has assumes a large relaxation between the degenerate orbitals. And much like the green figures, what's up? Much like the green figures that Ulan was showing, the blue figures we see our axis components for the range, and then the mesh component here is what actually is the figure. Any questions? So then this figure is the time integrated plot of this. So if you look, the blue figure on this graph corresponds to this specific one that I'm showing here. So this is just taking a time integration of the various. Oops, that's not going to work for this. The various emissions that were the variables that were used to plot the previous graph. So if we go here, you can see where I place them side by side, that the intensities line up with these whiter bars in the blue figure, because they have the same y-axis here.
David, we have a question. So Kia raised hand. Probably she wants to ask something right away.
Sure.
Could you please go to the slide 4?
Slide 4?
Slide 4, yes. So there we are able to see the blue line, bluish line, the from 2.5 to 3 there. Yes.
This one?
Yes. And then again there is no line there, and it started from, then again at the end of the, yes, there is another blue line. Why these things happen?
So
is it your question why they are not connected to each other?
Yeah, why they are not connected to each other. And again, you see, after below the 0.5, there is another blue line.
So my interpretation. So this, I'm going to switch to this one.
Okay.
So this is the same figure. I just joined the two figures together so you can look at them side by side. So this line right here is the same as my initial excitation, about 2.8 eV. So that's that would be indicating a transition from LUMO +3 to HOMO -3, if I remember the conditions I used for this graph. And then this one is at about 2.1, which is the band gap. So that would be HOMO to, or LUMO to HOMO. My interpretation of this one is that it's an intra band excitation. So it's at about 0.3 eV,
Okay.
which is the difference between LUMO -3 and -2 to LUMO +3 and LUMO, because my orbitals are degenerate, so there's 2 for each energy.
Okay.
So as for why they're disconnected like this is I don't offhand have the green figures for this model, but I'm assuming there's radiative or non-radiative processes going on between two sets of radiative emissions here.
While we are speaking, maybe Aaron, would you please find relevant slide in your thesis presentation and share it so that you just show equations for these figures?
And yeah, and I did not write down the equations when I made this graph or made this PowerPoint. I can get you the equation for this one pretty quickly.
No. We need it intentionally for the one that Kay is asking.
Yeah.
And if equations will be displayed, we can discuss and convince her that it is correct and reasonable?
What's the right equation?
So maybe equation for time-dependent emission. Oh, okay, okay, yeah, David did it. Okay, perfect, thank you. So would you please maybe move them this one to the left? Yeah, this one for this panel, this one for this one. For the blue panel, can you explain each term in the equation? And then the answer to Kia's question will be self-evident.
So this Fij is our oscillator strength.
Mm-hmm.
Yeah.
The delta, this is the delta function comparing the energy of the with the this is the delta function looking at
Actively populated orbitals, something like that.
yeah, it's the I'm trying to think of how to explain this and it's not coming to my head. This is looking at orbitals, different orbitals as they relate to time. And so this.
Let's stop and discuss first equation first.
Sure.
So what would happen to this equation if you remove oscillator strengths or replace it with one?
We'd get a big single color.
Would it go more continuous from the?
Yeah. More continuous. That's
do you get it?
That would be a good better way.
So there is a stripe that Kea did ask. The one started at 2.7 and then going from left to the right. Then it is broken, and then new stripe starts at 1 at the height of 2, right?
Of 2.1.
Yep. So there are definitely something between them, but it is dark because the multiplying factor, oscillator strength, which controls darkness or brightness of a transition, depends very much on the pair of orbitals. So initial pair of orbitals is bright, and final pair of orbitals is bright, but intermediate pairs are dark. They have vanishing oscillator strength. Therefore, we have a gap between these two stripes. Kay, does it make sense?
Yeah, a little bit.
Okay. David, sorry for interrupting you. Please continue.
So as for the second equation, so we take the result of the first equation and we integrate it with respect to time. Which gives us this figure, which the time integrated intensities.
So only bright transitions are observed.
So this is where we see the bright transitions and how they relate to time. So despite this transition at 0.3-ish EV looking about the same size and intensity as this transition at 2.1, the 2.1 happens over a much longer period of time. So it is a much larger peak.
The log scale.
Yeah, I'm trying to remember where.
It looks like log.
Yeah, it's log scale. So it's, I apparently need to change the labels on the axis because I don't write that, but yeah, it's log scale.
Okay. Anything else to this story, or it is kind of like last slide?
So that was my last slide. If you have any questions, we can.
Okay. Yeah,
continue.
please join me in thanking David. And let's check if there are more questions. I see there was a comment from Aaron. It may be not a question, but a comment. Aaron, would you like to verbalize it?
Yeah, it's just to make the data look nicer. You can, I think you can write like a quick little loop that will remove all of the bytes.
This one?
Yeah.
I purposely chose this one so that we could see that error was there.
Okay.
But yeah, there are methods to remove it.
And this is very interesting feature. I was recently given a talk at a conference, and these features induced active discussion of experimental collaborators. So the opinion is that it could be really new spectroscopy if one makes experiments at close to 0 Kelvin. But at elevated temperatures, there is very intense emission from regular infrared spectroscopy, just exciting and de-exciting molecular vibrations, which will screen this effect and just will create a noise that will not allow to find these features. So at regular conditions in this spectral range of very low energies, there will be much bigger signal from regular infrared transitions. So let's check if there are specific questions to David from anyone, from Sean, Samir, Kea, Amir, Steven, Sarah.
I might have missed this, but why is there that like dulling of the yellow at roughly -1?
I have no idea.
Okay.
It's indicating there's a loss of intensity there for some reason, but I really don't know what that reason would be. Because that's an artifact of the code, pretty much.
No, it's not an artifact. It could be an observable feature if experimental instruments are have fine resolution. May I ask Kea to share her slides once again, and David, stop sharing for a time.
Where is my mouse?
So, Professor, I think when David shows his graph, he chose different value of IE and IE.
Oh yes, and you are describing different systems, but now we are speaking about proof of concept.
Yeah.
So
he used the different values, right?
Yeah. Let's go to maybe 16.
Just
forward. Yeah, stop. Back. Yeah, this is a really good slide.
Okay.
So there is a cascade of little peaks in the time area between on a logarithmic scale between 1 and 2. So the energy cascading down from 4.5 down to about 1 electron volt, right? And the yes. Let me request.
Yeah.
control and try to draw.
Yeah, now you can draw.
Okay. So there is a transition from this excitation to this, and this transition happens by releasing some energy, delta E. So this energy can be released either into heat or it can be released into infrared emission. But then this infrared emission will happen on the very low frequency, which will be like 0.3 electron volt. Then when we go from this excitation to the next one, it releases another portion of energy, delta E prime. And then again, it can go into heat, into lattice vibration, or into infrared emission. And the same story for each of this pair of peaks. Sorry. Can you go back?
This.
So at each time step, it will be different pairs of excitations involved into this cascade. And there will be different transition energies and different intensities of infrared emission. So even if the energies are very similar, the intensity for different pairs of this excited to excited transitions emission will differ and will have different intensity. So the little drop in intensity for the data that David was showing is quite natural. I'm more surprised that it happens once. I would expect that it will be increasing and dropping several times. Okay, if you want, you can stop sharing.
I think this will happen because we use the same value of I, E, and I, E. The electron, initial value for the electron holes, we use the same values for 5, like 5.
Mm-hmm.
But the David, suppose he chose, he fixed one, like homo is 1 and other one he changed it.
Yeah, but there is another big difference. Your couplings and your data are computed for polyacetylene. David, we just keep, because we are covering just practical aspect. David is computing it for thin film perovskite, wet halide perovskite. It's drastically different materials. And their optical properties are very different. David, would you like to share your screen once again, just in case if there are more questions? Just final call for questions. Oh, yeah, thank you for bringing that.
I don't know, am I muted? No, I'm not. So this is the model. Yeah, that's the right one. This is the model that this is all on.
Okay. So let's make a final call for questions to David or to any of today's speakers. More questions 1, more questions 2, more questions 3. Let's thank all speakers and